Today we're going to talk about reverse mode AD, a little bit of theory, and then we'll show some examples in code in Julia. I find that sometimes, certainly in optimization class, we cover AD, but I spend more time on forward mode AD. It's a little more intuitive, and so reverse mode sometimes gets not as much attention, and it's really important that we understand this. We use this a lot, so we're going to take a little time today. I find that sometimes it's confusing when we try to think of the entire chain, but we'll find that it's actually quite straightforward if we just think about one little block and then it's that same block over and over. And sometimes when we're doing forward and reverse at the same time, we kind of mix up our numerators and denominators, but today, since we're just doing reverse mode AD, hopefully this will feel relatively clear. Okay, so let's imagine I've got some program, takes in some X and a bunch of stuff happens. I call other functions, those functions call functions. I've got loops and solvers, all sorts of things. And I get to the end and I return something. So what we can imagine is that I've got some computational graph. So I start with X and this goes through some operations and those go to other things and those call other things and go all over the place, and some of these come back together, and maybe those get other things, and so on. And then eventually, all these things come together, and I'm going to spit out some output J. Okay. For now, we're going to assume that J is a scalar, but we'll relax that a little bit. And X is going to be a vector. So in our optimization context, this is going to be our design variables, things that we care about at the very beginning. And this will be our objective and constraints. But for now, we're going to assume there's no constraints, just an objective. So just a single value. And you'll remember from the AD discussion that this would be likely a place where reverse mode AD would be advantageous because, especially as X gets bigger, remember that I've got to go forward mode AD once for each element in X. And in reverse mode, it's once for each element in J here. And since I only have one J, in this case with a scalar, I only have to pass backwards once, okay? So let's zoom in now on one operation here. And I say operation, these could be anything. So in a general purpose reverse mode AD, these are typically individual operations like adding two things together, multiplying two things together, taking the cosine of a number. And since I have all these little building blocks, I can now compose them in complicated ways, but I know the rule, we call this a rule, meaning how do I propagate a derivative through this? We know how to do that for each little block. So as I add more and more of them, I can just propagate it through any arbitrary one. But they could be also more complicated things. Maybe this is a solver. We'll talk about that later, not today, but in another video. It could be, a bunch of things. And actually, we'll make an example today with a few things just to illustrate. So let's say in this block here, I've got, let's say Y and Z come in and A and B come out. Okay, so that's just this one block here. If we can understand this one block, we can understand any block. And just to make up some things, we're gonna make up an operation. This is obviously not a real thing. It's just gonna be something silly here. It's gonna be, say Y squared times Z, and B is Y times the cosine of Z, just for example, just some made up operation. Well, the forward part will be quite natural to you, meaning if I know Y and Z, I can go in this block and evaluate A and B and continue on my merry way. In reverse mode AD, what we're going to do is we're going to know what's on the right-hand side, and I'm going to call this A bar and B bar, and we're going to go backwards, and I need to figure out what is Y bar and Z bar. Okay, so in forward, we went this way, but in backwards, I've got these things with bars, and I go from right to left. Okay, so those A bar and B bars are my inputs, Y bar and Z bar are my outputs. So for now, you're just gonna have to trust me that we know what A bar and B bar are, but it shouldn't be too surprising. We'll see a little more specifically, but in this case, how do I know what Y and Z are? Well, I start at the very beginning with some known X and I propagated through a bunch of stuff. And when I got to this point, I know what Y and Z are. They're just numbers, okay? Similarly, here I'm gonna start at the very back. And when I get to this point, I did a bunch of stuff, but now I know what A bar and B bar are, and they're gonna be just numbers. This is point where sometimes people get confused and they think of, oh, they're derivatives, so they must be symbols. Now they're just numbers or vectors of numbers, right? Right now I'm just going to look at scalars, just keep it simple, but vectors, matrices, they're all the same. Same ideas. In fact, I might do a matrix example as well, just because that came up today. But let's see what I was saying. So A bar and B bar. Sorry, I lost my train of thought. But anyway, when we get to this point, again, we know A bar and B bar, and we're going to calculate what Y bar and Z bar are, and they're just numbers. Oh yeah, I was going to illustrate why they're numbers. Just like in the forward one, I could potentially think of Y as this big, complicated expression, right? Like I took all the symbols of all these things and I jammed them together, and whatever was in Y, I stuffed it in here. And I took whatever stuff was in Z and I stuffed it in here and made a bigger symbolic thing. And I kept passing that forward. And when I got to J, I got this massive symbolic thing that I could evaluate, but that's not how we run computational programs. That tends to blow up exponentially, especially as we have loops and things. So what we do is we give numbers, right? I start with some numbers for X, and I go through here, and Y is just numbers. The same will be true for A and B, right? These are going to be numbers as I go backwards. I propagate derivatives, but I'm really propagating numbers, right? I'm propagating derivatives at a specific point, which is what we want. Okay, so for the time being, forget about what A bar and B bar, how we got those, but just accept that they're inputs, just like Y and Z are just inputs. Let's compute them. Let me define this bar quantity. So by definition, some variable C bar is equal to dj dc. This is going to be the definition, where J is the output at the very end, right? So it is nowhere in this block. It's just the thing that I care about at the very end. What's the derivative of that with respect to some local variable? Okay, and that's just, we'll call that bar. Okay, so again, A bar means the derivative of J with respect to A, and so on. So let's just derive now formulas for Y bar and Z bar, because again, I know these, I want to compute these. So Y bar, and by the way, this would be a good time for you to pause and try this for yourself if you'd like, but let's just go through it now. Y bar is, by definition, right? It is dj dy. That's the thing I want to compute. So let's compute it in terms of things that I know, and these are the things that I know, A bar and B bar. So that is dj dA, which is, again, this is A bar. And then just by the chain rule, dA dy, but because I've got two outputs, right, I got to continue with the chain rule, right? This is now dj dB. Again, so let's think about this. J depends on A and B, right? A and B come through here and they traverse through whatever they happen to traverse to, but eventually they end up at J. So I've got to include both these things, chain rule here, and then dB dy, right? And this is B bar, going back to the definition. So this is A bar, this is B bar. Those are the derivatives of the thing that I want eventually with respect to A and B. And those are things that I know. And now I just need to compute derivatives for my one little operation here. Okay, I don't really care about what's happening everywhere else, just this one little operation. What is dA dy? Well, I can just look at that and say that that is 2 times y times z. What's the derivative of b with respect to y? That looks like just the cosine of z. So if I put this all together, I have y bar is a bar times 2yz plus b bar times cosine of z. All right, so a couple things that you might pick up, how reverse mode is different than forward mode. One thing that's different is when I'm going forward here and doing forward mode AD, just like I'm doing forward mode just evaluation of the function, when I get to this point and I know what y and z are, I don't really care anymore about the details in the past. I can forget all of that, wipe that from my memory. Because once I know y and z, I know everything I need to know to continue moving forward. And that's not true in reverse, right? Once I know A bar and B bar, that's not enough. I actually need to know other things. I had to save the values of y and z so that when I come back, I can use those correct values so I can continue to propagate derivatives. And maybe I don't even save y and z. Maybe I save some intermediate values like the cosine of z. That won't really matter in this case because it's such a simple example, but I have to save some things, right? So the other difference is when I go forward, similarly, right? As I get to here, I don't care about the structure. I'm uncovering the structure as I go. So I get to this line, I say, oh, I want to call that function. Let's go there. Okay, now I'm on this line. Oh, I want to call this operation. Let's do that. When I go in reverse, I have to have saved something. I can't just look at what the output and says, oh, that must have been called from this function. I have no idea, right? I need to save this or record this as I go forward. So this computational graph, often in AD, we call this recording the tape. So like recording an old cassette tape, as I go forward, I'm discovering what's happening and where the functions are going to be called. And when I get to the end, I've recorded that tape. And so now I can play it backwards and traverse back through here. So both those things require memory, right? I'm recording this tape and I'm also recording, saving some of these values. So this is a more memory intensive. So even if J is smaller than X, if it's not much smaller, I still probably will have an advantage with forward mode. But as that disparity grows, then reverse mode will become advantageous. Okay, so that's really the main idea here. Relatively straightforward, but let's do 2 more examples here. I'm going to do an example that we're going to use today. And this is going to be an example where I'm going to have a function, we'll call the output A, and it's going to be a sigmoid function. So it's going to be 1 over, let's say 1 plus e to the minus c. Okay, this is a sigmoid function. And this is something that reverse mode AD can already do. So for example, in comes z, out comes A. Reverse mode AD can already handle this operation because it knows how to negate things, it knows how to take the exponential of something, it knows how to add things and divide things. So all this will just work. But today we're going to provide a rule, and this is a simple example. It's not really going to speed things up because it's so small, but I know the derivative of this whole thing directly. So actually, analytically, this is easy to show that the derivative of A with respect to Z is actually just A times 1 minus A. And since I have to compute A anyway in this process, I'm going to save that, and then I can compute this derivative without having to go through these intermediate steps. Again, simple example, but you can imagine more complicated things where there's a bunch of stuff happening, but I happen to know the derivative. We'll see an example with solvers in a later video where this will come in, but we just want to give this as a preliminary today. So let's do our rule because we're actually not done here. I don't want just d A dz, but I need z bar going this way now. I know a bar. Oh, and by the way, I forgot to tell you how we know these bars, so I'll go back to that in a second. I know a bar, I need to compute z bar. So z bar is by definition dz, dj, dz, which is using what I know, my input, dj, dA times the chain rule, dA, dz. This is a bar, which I know, and dA, dz is that thing that I just provided there. So z bar is a bar times a times 1 minus a. Okay, great. So we're going to use that today. And the idea is that we're going to provide a shortcut. So the AD thing already knows all of this, but I'm going to say, rather than letting AD do all of these individual operations like adding and dividing, I'm going to say, if you ever see this function, you can just jump over those things because here's the derivative. And we're going to do that in code today. So let's go back, and I said, well, I know what a bar and b bar are. How do I know that? Well, just like I knew what x was at the beginning, and I propagated that forward to get to some point, and now I know y and z. I know what j bar is, and as I go back, then I'll know these things. Well, how do I know what j bar is? Well, let's go to the definition. J bar is by definition dj, dj, which is just 1. Okay, so I start with j bar is 1, and I propagate back to this node, and I get the bars out of here, and eventually when I get to here, I've got a bar and b bar. So that's if j is a scalar. We can generalize this to a vector, which then represents any number of inputs. So let's say j actually looks like this. It's a vector, j1, j2, and so on. Well, then what would still happen is I can still think of this individual operation is I'm looking at a scalar. So let's say I'm looking at, because I have to do this one at a time anyway, right? I got to do this once for each output because I'm going to get different derivatives, sets of derivatives. So let's say I'm doing the J2 one. As I work my way back, I'm going to get the derivative of J2 with respect to all of my inputs. So when I'm at this node here, from my point of view, nothing's changed. I just have a derivative of a scalar, J2, with respect to A and B in this case, right? That's what A bar and B bar are. So how do I initialize J bar in this case? Well, in this case, J bar is equal to the derivative of J1 with respect to J2, which is 0, the derivative of J2 with respect to J2, which is 1, and then everything else is 0, right? So in other words, to initialize, I first start with a 1 and then all zeros. That gives me the derivative of J1 with respect to everything. Then I go 0, 1, all zeros. That gives me the derivative of J2 with respect to everything, and so on. Okay, so I'll do one last example just because this came up today in our group meeting. And this is just going to be a matrix case. So let's imagine I've got a matrix C equals A times B. And this is already going to be a rule that's provided in your reverse mode AD. We just did this as an example for something more complicated that isn't already provided, but just to motivate, so that we don't have to have scalars. Generally, we're going to have vectors and things. But this is a matrix case. There are many ways to derive these rules. Most of the time, for me, what's most convenient is to use index notation. I like index notation because then everything it's easy for me to look at. Things become scalars because really when I take derivatives of vectors or matrices, then I'm going to get higher order tensors and things. So if you haven't seen index notation, really all we need to know for now is that this index just means this is the ith element of a vector. So ui is just a vector, whereas aij represents a matrix, right? And if I have two repeated entries, so if I had like ui, vi, that's a dot product. So this is an implied sum, right? It's summing over those. And so if I have, actually this case here, cij would be ai, right? Because the size of the first element of A needs to match the size of the first element of my output, and then K times BKJ. So if you remember the rules of matrix multiplication, the size of here is going to match the size of here, and the size of here is going to match the size of here. So those indices should match. And then this K is a repeated sum, right? And those dimensions should match to do matrix multiplication. So this is just the rule. Like if I was doing this in a for loop, right, I would say Cij is equal to, well, I'd do like a plus equals or something, and I would do aik, bkj, and I'd be looping over all k, right, and so on. So anyway, this is just matrix multiplication written in a index notation. Okay, so let's imagine our block. Draw this thing. It helps me to draw this sometimes. A and B come in, C comes out. So think backwards here. C bar is what I know, and I want to get A bar and B bar. I'm just going to do one of these. So let's do A bar. It's going to be equal to, by definition, dj dA, which is, let's expand this in terms of what we know. We know dj dc, that's a given. And so here's where I need to be more careful, right? So let's now put in my indices. Otherwise, we're going to get really confused because I'm going to take a derivative of matrix with respect to matrix. And we're going to say, well, what is that? But if we do it all in terms of indices, these are all just scalars, and it's pretty easy. So let's use the same indices I used before. So A bar ik is going to be dj daik. And so that's going to be dj dc ij. I'm going to use the same indices I used for C and for A. And then by the chain rule, right, this is going to be dc ij with respect to daik. So by definition, this is C bar ij. And well, what's this? Well, that's easy because dcij is this term, daik is this term. So the derivative is just this, right? bkj. So this is a matrix product, but we have to be careful, right? Remember when we multiply matrices, the summation has to be on the inside. So we can see I'd have to transpose B. And then the indices line up, right? Because the I is on the outside here. The K would then be on the outside here. So that all checks out. So A bar is going to be C bar times B transpose. Okay, and similarly for B bar. All right, so you can forget all that if that was confusing, but for now, today, I'm going to focus on this part, which is we're going to provide a rule in our code and see how that works. All right, so as I jump over here to the code, there's kind of two things I want to show. One is just, kind common issue, one common issue we run into, sorry, is you're trying to use reverse mode AD, specifically with reverse diff, and then also just how we can provide a custom rule. All right, so for this example, I'm doing a really simple neural net. And if you don't know what that is, it doesn't really matter. But if you're interested, I made a video last week about DNNs, and you can go find that in the optimization playlist. But since we talked about this a little bit as an example in the group meeting, I'll just explain briefly what's happening here. Again, this will make more sense if you've seen the video. If not, it won't matter for what we're trying to understand today, which is just how to apply reverse AD. I just need sort of a concrete example to start with. So here's a neuron, and if you remember what happens in the neuron is that we take all the numbers that are coming from our previous layer, we apply a linear operation. So this is just a matrix of weights, and then we add a vector of biases. So this is all linear, and then we pass it through some nonlinear function. And I've got two here. The most common one that we'd use is this ReLU nonlinear function, which just takes a max of 0 and whatever you pass in. And then there's a sigmoid function, which we already talked about. That's another one. So our network is pretty simple. You have some inputs coming in, which is a matrix because it's a vector for one data point, but then we've got a bunch of data points. But anyway, we just go through each layer in the neuron and call the function we had before, and we do that a bunch of times just using a ReLU. For the last layer, we're gonna do a classification problem. So we're gonna try to push these numbers towards zeros and ones. So we're gonna use the sigmoid function. And then our objective is we're gonna take all of those predictions here, compare them to our known values. This is gonna be just a binary classification. So these Y's are gonna be zeros and ones. So we're just gonna pass it to this cross entropy function. Doesn't really matter if you know what this means, but this is just a maximum likelihood. So I'm trying to maximize the probability that what I predict matches what is actually in my training data. So anyway, that's the network. I've got some initialization here, not really important, just initializing these weights and biases. Okay, so the only other piece here is, actually, let me just run this first real quick. So, okay, yeah, I just ran it. So what I'm doing here, I'm just saying I've got a neuron, a network with 3 input variables, a hidden layer with 4 nodes, and then just 1 output layer, or one node in my output layer. Okay, and I initialize my weights and biases. Here's just some random data. And these are just my labels. So these are my known things. So this is binary. So let's say I was just trying to, I don't know, just do like a image classification. I was trying to figure out, is this an animal or a person? And a 1 is a person and 0 is an animal or something. And these are my known things that I'm trying to train on. And I pass it in and I got my objective. So again, none of those details are really important. What matters from our perspective is that I've got some output J, and the things that I want derivatives with respect to that I optimize are actually these weights and biases. These are the design variables in my network that I'm trying to change so that I get better predictions. And so this is a common thing that we have to do when we're doing optimization, is that I may have a bunch of structs or different data structures that I've come up with. In this case, these are, it doesn't matter for to know, but these are vectors of matrices and vectors of vectors, because the W's have different sizes between the different layers because I've got different number of neurons in each layer. So what I'm going to do, though, is I'm going to concatenate all of these things into one big vector. Some reverse mode packages, we can keep them in matrices and things, and maybe even sometimes in structs. But in general, when we get to the optimizer, we usually have to put these all in one big vector anyway. So that's all that these 2 functions here do. So the first one says, give me all your W's and B's, and I'm just going to concatenate them into one big vector of X. And the other one does the reverse, says, give me your vector of X's, and I will put them into the W's and B's. And this is just kind of a common thing. We do in optimization, which is, map some vector of design variables to our data structures and then maybe go backwards, right? So that's all that those are. So let's just do reverse mode AD. So we're going to use reverse diff. And I need to write some wrapper function because actually reverse diff can handle a matrix, but I don't know if it can handle a vector of matrices. And actually I've got 2 vectors of matrices, so I'm pretty sure that's not going to work. So what I'm going to do is I'm just going to write a wrapper function. I'll just call it wrapper because I'm not very imaginative. So it's going to take in a vector of inputs. And I'm going to call my function this it turns those back into my own data structure, which is W's and B's. Okay. And then I can call my function that evaluates my objective and maybe other things. And these X's and Y's are fixed. So I'm going to just keep them from here. Note, this is a global variable. It's not really the best. I'm just keeping here for, normally I should put this in a function and maybe we'll just call it our main function or whatever. But I'm just not going to do that today. I'm just going to keep this simple. But for performance reasons, this is not desirable. Anyway, but X and Y are defined in the outer scope. They don't change. They're just fixed things. So I've got W and B, I compute J, I return J. So this is the format we'd normally expect from an optimizer: vector in and then vector out. But in this case, it's just a single objective, no constraints, simple problem. Of course, we almost always have constraints in our problems, but in neural nets, they're almost always, they're just an objective. So that's what we have today. Okay, so let's try this. Actually, let's just call the function to make sure it works. But what's X? I haven't set an X. So let's just take my other function, this one, that makes an X for me. So let's take the W and B that I initialized to right here. We'll call that X0. And then let's call our wrapper function and make sure that works. And it's just compiling. And that works. So that was kind of slow because it's compiled, but you see if I run it again, it's still slower than I expected. But anyway, I'm doing global variables and a lot of bad things. But here we go. There it is. There's my objective. So let's now call reverse diff. So let's look at the documentation real quick. In this case, well, we almost always want Jacobians in our lab because we've got many outputs, but here we only have one output. So it's just a gradient. And if you use this, you should get familiar with these other ones. You're going to get better performance and you can pre-cache things and compile tapes and so on. But keeping it simple today, just the simplest possible call. We're not even going to worry about this optional thing. We're just going to let it do it for us. So we just need a f, which is some function that looks like this, meaning it's a function that takes in a array of things that are real valued and spits out something that's real valued, right? So it's a many to one, it's a vector or a matrix to a scalar, which is what we've got. And then input, which is just an array, right? That's where our starting point or our evaluation point. So that's easy. Reverse diff dot gradient, and I give it my function, which is my wrapper, and I give it the starting point, and this is going to be my gradient. So let's see if that works. And it does work. Oh, great. Yeah, that's because I already fixed what I was trying to not fix. Well, I fixed it for you, but okay. So let's say it didn't work. Ignore what I did there. Okay, so I got an error, and this is going to be a common error you'll get with both forward and reverse. It's just a type thing. So let's read the error. It says, you're trying to convert a reverse diff, tracked real, blah, 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 some reverse type to a float type, and that's not defined. So this will be a common thing also when you're doing forward diff, meaning you've initialized something to have floats, and I've got this type that's not a float, it's a reverse diff type, and I can't put it in your container of floats. Or it's going to be a forward diff type that I can't put in your container. So when you're looking at these stack traces, sometimes people are like, well, I have no idea what's going on, but this is very helpful to read. And it's also very helpful to kind of look through here and figure out where is this happening. So this is going to be in reverse order, meaning this is the thing I called at the very top. So if you command click on something, or probably control or something in a different operating system, if I highlight over it, it says command, it'll take me to the line of code where the error was. And of course, this is the top level, so this doesn't tell me anything. It says, oh, the error was somewhere in here. And then I'm jumping in one layer and one layer and one layer. It's going to be very unlikely that my error is in reverse diff or some of these other packages. It's going to be in my package here and here in main. Actually, this is not a package, it's just a script here. But I should start in the back generally. First, here I'm in convert, reverse diff. These are not my stuff. This is in the array. So the first thing here is, oh, this is my function, x to params. And so the error is happening here, right? And if that maybe didn't clear it up, maybe I go up one level, but usually kind of that first level, is going to help me, one of these first two levels is going to help me figure out what's going on. So here's the issue. What's happening? Well, what I would do if I still wasn't obvious to me is maybe I'd go look at these types, because remember, I've got this type issue. So maybe it's, okay, what's the type of X and what's the type of W? And so I'm not going to print X and W, but let's actually print the element type of X and W. So type of is what's the type of X, but L type says what's the element type, meaning what are the type of things being held in X. So X is a vector of something. What is that something? And W is a matrix of something. So what is that something? So I run this again. It says X is a matrix of reverse diff stuff, as I might expect, but W is a matrix of floats. And so whatever happened here was a problem because it didn't, computed a bunch of reverse diff stuff and tried to stick it in W, but W says I contain floats. So I don't know how to put that in there. If I still, like if that didn't help me, maybe I break this down and I start looking at different pieces, right? Like maybe this has multiple things happening in one line. So maybe, this is just kind of a crude debugging thing, but if I know it's this line, maybe I break this down into different steps in this line. Was it a problem with this part? Did it not like the reshape part? Did it not like the allocation part? And I'll find that, okay, well, actually I did not mean to print them, but that's also fine. I was just gonna call those things. So get rid of the prints. And I'm just going to run all those operations. So like if this was a problem, I would get the error to happen here. But as I go back to where's my error, it still takes me this line of code. So all of this was fine. The last problem was this assignment. So yeah, we see that W is initialized to floats. So I didn't write this generically enough. So one thing I could do is I could set up a type. I could pull out what is the type of X. So as X gets passed in, maybe X is float because I'm not doing differentiation, and maybe it's a reverse diff type. Maybe it's a forward diff type. I don't now want to hard code it to be this reverse diff type because maybe I'm going to do forward diff later, or someone's going to do that, or I want to just call it with floats or other things. So here I'm going to call, and T is just a variable name. I'm just saying whatever X came in, pull out the element type, and let's put that in here. Let's now initialize W and B so that they have the same type of whatever X is. So now if I do that, this should be happy, and I got my gradients. Great. And I often want to check those. So let's just take forward diff here and compute a gradient again. And let's just maybe subtract those. This is an infinity norm. Let's look at the maximum. Probably a shortcut for that, but it's the maximum absolute value for the difference between those two, which is the infinity norm of the difference. And that is machine precision here. So below it. So they're exactly the same. To machine precision, so good. My gradients are correct. Okay, so that's all well and good. What I want to do now is I want to add my custom rule. So here's my sigmoid function, and the output of this is A. And remember, everything is working fine, but I know the derivative of this, so I'm going to actually provide it. So the way to do that, we're going to use a package called chain rules. Chain rules core, but I think it's in this chain rules package. So let's just pull up chain rules, go to the docs. Yeah, so here's chain rules. And so the main idea of chain rules briefly is that there's a lot of AD packages, and here shows a bunch of them. And we talked about how we got to provide rules for everything, and it's not really ideal for everybody to have to keep providing new rules for every AD package that has different, kind of pros and cons. So let's define these rules in one place, and then as you come up with a new AD package, you can go reuse these rules, and that'll be great. So here's a place where we can add new rules. And so let's just look at an example here. We're going to basically copy and paste this example here. So, oops, no, that's fine. I'm going to put this here by the sigmoid function. And I obviously am going to need chain rules core. I've already added that package, but if you haven't, you'd have to add that package. And so this is saying I can define a new rule for some function. Here they're defining it for this function they called foo multiply. I want to define it for a function sigmoid. And notice this first argument is the type of it. Normally, if I wanted to use this, I'd have to put something here, like this is my function here, but I don't actually need that anywhere in there, so they just left that out. And then the next two arguments, foo and b, those are arguments to that function. And so in my case, the only thing I have is z. I don't need to put any type, so z, that's all I've got. And I'm going to define a rule. So the first thing I do here is I define the forward path. So here they just called foo like it would be normally, and this is where I'd cache anything that I want. And so for my case, I'm going to say A is sigmoid of Z, make it a capital A. This is an element-wise thing here. So I derived it before for scalars, and that's actually going to work because we're just doing everything broadcasting. Everything is going to be element-wise multiplied. So this is fine. This is going to work as it is. So I'm going to save that A. And here what I return is that output A. That's what just goes in the forward. And this next part, this function, I return what's going to happen on the output. And so let's get rid of all this stuff. And I can call it whatever I want. I can call it sigmoid. Pullback is a name that's often used for these as we, that operation where I give you the bars on the right and you give me the bars on the left. I'm not going to use the Unicode because I think that's a little bit harder to read in that particular case. So I'm going to call this Z bar, right? That's what's coming into me from the AD package. It's got that graph, right? And it worked from the beginning with J bar. And at this stage, it's got Z bar and it wants me to figure out what's A bar. So if we remember our rule, it was, and I don't totally remember, I'm doing this by memory here. I think it's C bar. No. I'm doing this backwards. Sorry again, right? That's why I always draw this. Z comes in, A comes out. So as I go the other way, A bar comes in, Z bar comes out. So A bar is what's coming in, and I want to return Z bar. Okay, so Z bar is going to be equal to A bar times A times 1 minus A, and I want all of this to be done element-wise. These are all element-wise operations for this particular function here. This is an element-wise sigmoid. So I think that's what I want, and I got to change the name of this since I changed the name of my function. And I'm going to put a print statement in here just to make sure this actually got called so you can see if this works. Okay, so in general, this is all you'd have to do, but since chain rules was made later than reverse diff later added the option to use these, but it's not, we have to add one more line to make this actually work because it wasn't adopted. But if you're using a different reverse mode AD package like Zygote, I think that's all that you should have to do. I don't think this is really documented in reverse diff. You just kind of have to search this. And it is in some of the issues. You could find it here. You could also find it in some of these discourse discussions on the Julia discourse. Yeah, it's this thing that you got to use, this decorator here. So I actually have to tell reverse diff, add this rule for me on sigmoid. Anytime I've got my Z that is, actually, maybe that's all I have to do. I could say it's a tractor array of reverse diff types, but I think this is all, maybe this just works. We'll just see. This might be it. Okay, so let's try it again. Tractor array is not defined. Oh yeah, of course, because it's a reverse diff. Actually, I'm pretty sure what I have is not going to be a tractor array. I want an abstract array of tracked reals, because that was the type that I've got here. I've got these tracked reals. So there's some subtle differences there I'm not going to get into today, but in this video. Okay, so you could just copy and paste this if this would be the most common thing you do. Actually, if you wanted to, you could do both. This is what I often do. I think it's reverse diff tracked array. Is that what it's called? Either one of those. Okay, so let's run this. So I've defined the rule in either case. And somehow I messed up. I did call pullback. Input derivs is a tuple. Oops. I don't want to go into my macro. Where does this land in my code? This is going to be, see, this is where it's a bit hard when it's a macro. Sometimes it's a little bit hard to see where this is. I might have to cheat and look at what I already did. Oh yeah, duh. Okay. There are two arguments here, so I should have been so quick to delete everything. Notice they return three things here. That's because there's three arguments here. And so I have to pass this thing that's called no tangent. These ones are sometimes hard to debug when they're in a macro, but this is saying what's the derivative? Okay, I need the bar of everything. So I need the bar of z bar. I need the bar of this function name, but I don't have that. Like that's not an operation here, right? So I'm just saying there's no derivative for that thing. So they called it f bar or whatever. Just call it whatever. It's nothing. Actually, I don't even call it anything. I'm just going to pass that here. Okay. And if I had other arguments, right, like in our first example with x and y and a and b, I'd pass my x bar and my y bar, or sorry, we had y bar and z bar. But again, every time there's going to be a function name. And so here, it'd be rare that I'd ever have some derivative. I don't even know what that would mean. Maybe there's some case where that makes sense. I'd have to think about that. But yeah, so I'm returning a tuple here, and that's why I got some issue about this tuple here. Okay, so maybe this will work unless I messed up somewhere else. Okay, great, that worked. And the norm is still great, so everything is happy. And notice, actually, did it? Maybe it's not happy. It did not, oh, it did. I just deleted my pullback, so I don't know for sure that this is happening. Yeah, there, see, it printed pullback, so it did indeed call this function and everything is working. Okay, great, so that's all for today. Like I said, the biggest thing that you'll run into with, I think, doing forward diff and reverse diff in particular is just making sure you get those types right. And then if you want to define custom rules, there are good use cases for that. We'll see an example later where we'll look at solvers, but just show you an example of how you can do that, define your own custom rule. Pretty powerful and relatively straightforward. This chain rules package makes that really nice. All right, see you next time.